In this lesson, I want to do a quick introduction to the gravitational force. Later on, we'll do a much more detailed look at gravity. But for now, we'll just give you a few basic ideas so that you can start using gravity in some of these Newton's second law problems. So gravity is a field force that's always attractive. It always pulls objects together. And it exists between any two objects in the universe, no matter how big or how small. We're used to thinking about gravity as only something that like planets and stars do, but everything has gravity. There's a gravitational force between myself and this pen. We're attracted to one another. Gravity is very weak though, unless masses are huge, so you're not going to see this pen suddenly stick to me. Force is way too weak for that to occur. Gravity only becomes really noticeable when you have enormous astronomical sized objects like planets, but it's always there nonetheless. So here's how the gravity force looks mathematically. Here are two objects. They could be any kind of object. It could be a planet and a moon. It could be a person and a pen. It could be you and the computer you're watching this lesson on. It doesn't matter. Any objects that have mass are going to do this. Let's draw a line connecting the center of those two objects and say that this has a length r, r1, 2, because it goes between objects 1 and 2. Now, Isaac Newton, among his many discoveries, figured out that the gravitational force equals this constant number called capital G times the mass of object 1, the mass of object 2, divided by that distance between those two objects squared. This number G is called the universal gravitational constant. And it equals 6.672 times 10 to the minus 11 newtons meters squared per kilogram squared. Notice that 10 to the minus 11 is a very small number, which is why you don't notice gravity unless one or both of those masses is very big. For most masses in everyday life that are maybe a few grams or a few kilograms, because you're multiplying by 10 to the minus 11, this force becomes so tiny you'll never notice it. But the mass of planet Earth, for instance, is like 10 to the 24 kilograms. So this force becomes important. Let's think about force vectors and Newton's third law now. So if these two objects are pulling on one another via gravity, that means that object 1 is experiencing a gravitational force from object 2. It's getting pulled directly toward object 2. That force is directed along the line connecting those two objects. And by Newton's third law, that means object 2 must experience the same magnitude of force in the opposite direction. Gravity force of object 2 on 1 is equal in magnitude and opposite in direction to the gravity force of object 1 acting on object 2. So Newton's third law is true for all types of forces, no matter what they are. Gravity, electric force, contact forces, field forces. It doesn't matter, it's always true. That means right now, as you're watching this video, maybe you're sitting in a chair, maybe you're walking around, Earth is pulling you down with a gravity force, but you are pulling up on planet Earth with the same amount of force. Okay, what else can we say? Let's talk about weight. Weight is the magnitude of gravitational force that an object experiences. Weight is not the same thing as mass. Mass, as we talked about a few lessons ago, is amount of substance or inertia or the gravitational charge. Weight is a force. This is just how we use the word weight in physics. We give it a different meaning from mass. In everyday language, people use these words kind of interchangeably, but in physics, weight refers to the gravity force on an object. So, in other words, weight is whatever this value is. And imagine that one of our two objects here is planet Earth, and the other is you or whatever objects we want to weigh. Then this equation would be G, mass of Earth. Sorry, you can't see that E very well. Mass of Earth times mass of object divided by the radius of the Earth squared. If you're standing on top of the Earth's surface, then the distance to the center is the radius. And you can write this G m, mass of Earth divided by radius of Earth squared times the mass of the object you're interested in. And this quantity, if you plug in those numbers, you plug in 6.672 times 10 minus 11 for G, you plug in the Earth's mass for M, which is 5.97 times 10 to the 24 kilograms, and you divide by the Earth's radius, which is, I think it's like 7,000 kilometers or something like that, squared. This quantity equals that number G, 9.8 meters per second squared, that we've been seeing all along in this class. So as long as you're near the Earth's surface, you can say that the gravity force you experience is your mass times G, 9.8 meters per second squared. So that's where G comes from. It's the value of these three parameters when you're on planet Earth. If you were on a different planet, there would be a different G value, because the planet would have a different mass and it would have a different radius. For instance, on the moon, not a planet, but still a large gravitating body, if you do this combination of numbers on the surface of the moon, you get a value of G that's about 1/6 the value of G on Earth. So that's why when you see videos of astronauts on the moon, they're jumping around really high. Gravity is much weaker there. This gravitational acceleration is only 1/6 of what it is on Earth. So let me do a quick calculation with you. This explores both the gravity force and Newton's third law. All right, assuming your mass is 70 kilograms, what's the Earth's gravity force on you? What is your gravity force? On the Earth? What is your acceleration if you fall? And what's the Earth's acceleration when you fall? All right. Part A, the Earth's gravity force on you. That's another way of saying, what is your weight? So the force of the Earth on you is your weight, which is mg, like we just talked about, or 70 kilograms times 9.8 meters per second squared, 686 newtons. Force is a vector. We're just kind of doing 1D, just along the up and down direction. So the direction of that force on you is down. Or if you wanted to pick a coordinate system, you could say it's negative y. What's your gravity force on the Earth? You can answer this either by plugging into Newton's gravity equation, or you could just use Newton's third law of motion, which says that the force of you on the Earth is minus the force of Earth on you, which would be 686 newtons up. The minus sign means to just flip that. Minus down equals up. So this is one of these weird but true consequences of Newton's third law. If gravity is pulling you down, that means you are pulling the Earth up. So let's say you jump off a chair or a table and you fall downward. What's your acceleration? Using Newton's second law, your acceleration is the net force on you, which comes from gravity, divided by your mass, or 686 newtons divided by your mass, 70 kilograms. Oops. that's down. And guess what happens when you do that? It equals 9.8 meters per second squared down. So that's where this 9.8 comes from that we've been using all along. So this is your acceleration. But we can do the same thing for the Earth. Because if you think of this being you and that being the Earth, you're both getting pulled toward one another when you fall. Falling is just two objects being attracted via gravity. So we can calculate how the Earth is moving too. The acceleration of the Earth, so that was you, and this is the Earth. It's that force of you on the Earth divided by the mass of the Earth. So it's that same magnitude of force, up this time, but the big difference here is that we need to use the Earth's mass in the denominator, which is enormous. 5.972 times 10 to the 24 kilograms, which gives an acceleration of 1.15 times 10 to the negative 22 meters per second squared up. So yes, the Earth is moving when you fall. It's also falling toward you. You're both falling. You're falling toward the Earth falls towards you. Two objects are falling toward each other. But your mass is very small. So via Newton's second law, you get a significant acceleration. The Earth's mass is very large, so even though it experiences the same magnitude of force, the acceleration it gets is tiny. You're never going to notice that acceleration. This is way too small to ever measure.